This is chemistry, and the first question from this page reads, study the diagram below and use it to answer the questions that follow. So I've been given here potassium manganate 7 in this conical flask labeled flask B, and there's a dropping funnel that delivers a liquid H dropwise. So there's a controlled amount of liquid H getting delivered into this conical flask to react with potassium manganate 7. Then there's this other conical flask connected to this first conical flask using what you call a delivery tube. There's a liquid C here, and just next to it is another conical flask that has concentrated sulfuric 6 acid, and from this end there's what you call a combustion tube that has aluminium on a crucible. There's then this other part that has a conical flask with a guard tube that has a solid A, and just inside this conical flask there is a solid U. So we are actually told to use the diagram to answer the questions that follow. So we've been told, suggest a suitable reagent that can be used as solid A. So first, we need to actually proceed and be able to interpret all that this diagram has to actually contain or have. So I'll begin from this end. Looking at this potassium manganate 7 and having this liquid H, what comes into my mind is that in most cases where potassium manganate 7 is found, there must be the preparation of chlorine gas. So on top of that, then that means potassium manganate 7 will actually serve as an oxidizing agent, and it ends up reacting with a particular liquid labeled H, and that liquid must be an acid, and that acid is called concentrated hydrochloric acid. So how do we actually write the equation between this potassium manganate 7 acting as an oxidizing agent and that acid placed in this delivery tube or this dropping funnel? So you're actually going to talk about this. You're actually going to say potassium manganate 7, okay, is getting reacted with dilute hydrochloric acid, or you can actually be able to get to that point of using it in its concentrated form, so that you can actually be able to have this. The potassium picks the chlorine to give us potassium chloride plus, then the manganese again picks the chlorine to give us manganese chloride. Then we have the hydrogen picking the oxygen to give us water, and lastly chlorine gas is able to get formed because that is our intended product that we intend to form in this reaction. So if we look at this equation, I'm supposed to balance this equation, and I'll literally be able to have 16 here, then 2 here, then I'll be able to put 2 here, okay, then I'll have to put here 2, and that gives us 4 plus 2, that is 6. So I'll actually be able to put here 5, then put here 8. This is a solid, this is an aqueous solution, this is aqueous, it's a salt, this is also aqueous, it's a soluble salt as well. This is a liquid, which is water, and this is a gas. So this is our balanced chemical equation that you're supposed to have in as far as whatever happens in this first conical flask labeled flask B is concerned. And after that, then that means chlorine gas has been formed. It escapes through this end. On reaching here, we need to have this scenario whereby you should understand this. Whenever potassium manganate 7 as an oxidizing agent reacts with dilute hydrochloric acid or concentrated hydrochloric acid, then at the end of the day, you'll realize that this reaction will end up producing heat. And that heat can sometimes also, in most cases, vaporize this dilute hydrochloric acid to form hydrogen chloride gas. So that at the end of the day, whatever leaves this flask B is one, hydrogen chloride gas, as vaporized gas from dilute hydrochloric acid and the chlorine gas that gets formed when the two react. The dilute hydrochloric acid and the potassium manganate 7. So to ensure that only chlorine gas gets collected on this other end, we can decide to put here either water or sodium hydrogen carbonate. So that any fumes of the vaporized hydrogen chloride gas from this hydrochloric acid used in this reaction can get dissolved in this water or in this sodium hydrogen carbonate. That is what happens. So you can put here water or sodium hydrogen carbonate so that any fumes of what we have as hydrogen chloride gas resulting from the vaporized dilute hydrochloric acid can get dissolved in that, so that the only gas allowed to escape through this end to this third conical flask is chlorine gas. How? For example, if this is water and we have to actually have this hydrogen chloride gas getting passed through this end, it won't actually find its way into this other end. Why? Because hydrogen chloride is more soluble in water. We are told that one volume of water can dissolve 500 volumes of this gas. Just imagine. One volume of water can dissolve 500 volumes of what? Hydrogen chloride gas. Unlike the other gas, now the chlorine gas, where only one volume of water can dissolve 3 volumes of the gas. So hydrogen chloride gas is more soluble in water than chlorine gas. So when they all reach here, hydrogen chloride with its higher solubility dissolves in the water to give us an aqueous solution, of course, of hydrogen chloride aqueous. Or you can actually have the fumes of hydrogen chloride gas reacting with the sodium hydrogen carbonate. So the fumes get absorbed. So they won't actually get allowed to escape this third conical flask in this setup. So the gas that reaches here is chlorine gas. So we have hydrogen chloride gas here and chlorine gas. Chlorine gas was obtained when this dilute hydrochloric acid reacted with potassium manganate 7. But hydrogen chloride gas resulted when this dilute hydrochloric acid got vaporized because of the reaction being exothermic. You see. And of course, even heating sometimes can get allowed for this reaction to get that point of action speeding up. And in that process, the acid can get vaporized. So at the end of the day, the chlorine gas reaches here. The gas reaching here has some moisture. It has passed just through this region that has water. And remember, the other part had an acid, which is actually a liquid. So at the end of the day, this gas must actually get collected when dry. How? The chlorine gas gets passed through dilute or concentrated sulfuric 6 acid. So concentrated sulfuric acid is a very good drying agent. It is hygroscopic, so it absorbs moisture from substances which are moist. So it being a hygroscopic substance, then that means it can absorb moisture from the chlorine gas, and that can make the gas to get collected when dry. Okay, the gas has been actually allowed to escape through this into the combustion tube when dry. Why? Because concentrated sulfuric 6 acid is hygroscopic. It has absorbed moisture from that gas, making it actually get collected dry. So when the gas reaches here, the chlorine gas reacts with aluminium to give us aluminium 3 chloride, and this is a sublimate. To mean we can allow heating to actually get that product introduced here, so that in the process, the aluminium 3 chloride being a solid turns into vapor directly. We said sublimates are substances that can turn from solid to gas without melting to form a liquid. So they don't go through the liquid states. We have aluminium 3 chloride, iron 3 chloride, benzoic acid, we have what you call iodine, we have what you call dry ice. You see, ammonium chloride, you see, they are actually sublimates. They turn into vapor directly without forming any liquid state. So the aluminium reacts with the chlorine to give us aluminium 3 chloride. And in the process, the aluminium 3 chloride can actually be able to sublime when heated, can actually be able to turn into gas when heated. So this aluminium 3 chloride finds its way into this other end, and on reaching here, it must first be able to get collected as vapor on the upper parts of this conical flask. But later on, after the cooling process, this can get again deposited as the solid aluminium 3 chloride. So it's possible for it to get collected as vapor or get collected as a solid, depending on the prevailing temperatures within that environment. And this guard tube has to have, for example, a calcium oxide. First, calcium oxide can actually be able to react with any excess chlorine which is actually not able to react with aluminium, because chlorine gas is a greenhouse gas. It can't get allowed to escape into the atmosphere. It can cause an adverse effect on the environment in terms of its poisonous nature and being able to actually cause what you call acid rain that might actually cause adverse effect to the environment. For example, corroding of metallic structures, damaging of stone buildings, and of course leaching of nutrients in the soil, chlorosis. Look at that. So all those can be effects, even increasing the acidity of what aquatic wet environment and causing harm to the aquatic animals. See, and of course, literally when the soil becomes more acidic and nutrients become leached, that can cause an adverse effect to the growth of plants. So there's what you call less growth rates and as well lower yields in terms of production from the crops. Okay, at the end of the day, we shall actually be able to realize that now the guard tube has to actually contain calcium oxide that can actually be able to, one, react with any unreacted chlorine. Look at that. Any unreacted chlorine can react with the calcium oxide, preventing it from escaping into the atmosphere. Number two, the calcium oxide can also be able to prevent entry of moisture into this setup. Why? Because when the aluminium 3 chloride comes into contact with water, then what happens? It forms aluminium 3 hydroxide and dilute hydrochloric acid. Just look at that. So that at the end of the day, we might actually end up having a challenge in terms of having our initial aluminium 3 chloride. So that is it. So we'll actually say that, so this is a solid, this is a liquid, this is an aqueous solution, and this is also aqueous. So the aluminium 3 chloride has to get kept free from moisture. That's why you can either use calcium oxide or calcium chloride, which is anhydrous, so that any moisture that may want to find its way into this conical flask is able to get absorbed by this substance getting put here. That's why it's called a guard tube, to prevent entry of moisture into this conical flask that might actually end up reacting with the aluminium 3 chloride collected, either as a solid or vapor, depending on the temperatures. Okay, so the first question, suggest a suitable reagent can be used as solid air. Solid air. We've actually talked about calcium oxide or calcium chloride. Any of these can be used, but the most appropriate one is calcium oxide. Why? One, it can react with the unreacted chlorine gas, preventing it from escaping the atmosphere. Two, it can absorb any moisture from the chlorine gas. So when the chlorine gets allowed into the atmosphere, it should be in its dry form, preventing the formation of what? Acid rain. And again, it can prevent entry of moisture into this conical flask, preventing any reaction between the moisture entering here accidentally and the collected aluminium 3 chloride. So the product gets prevented from reacting with the moisture. If you're talking about calcium chloride as well, which is anhydrous, then it means you're supposed to actually talk about, one, preventing entry of moisture into the conical flask that might react with this product, or drying the chlorine gas escaping, which may not have actually reacted with our aluminium in this combustion tube, so that the chlorine gas unreacted might get allowed to escape to the atmosphere in its dry form. Name liquid C and H. Liquid C is, you can talk about water. Yeah, that might be the most appropriate one, because you'd want to actually talk about a liquid in which the excess or the vaporized HCl gas can dissolve into, preventing it from finding its way into these other areas where the chlorine gas has to actually get collected, which might make chlorine to be impure. H is going to be dilute HCl or dilute hydrochloric acid. Write a balanced chemical equation for the reaction that takes place in conical flask B. I've actually captured here the question. You can think be able to see it. So there's a reaction between potassium manganate 7 and dilute hydrochloric acid to give us potassium chloride, manganese for chloride, water, and chlorine gas that has to get collected. Okay, and the equation is balanced with all the state symbols. Explain why solid U collects further away from aluminium metal. It is a sublimate. It easily turns into vapor because of the heating. So once it gets formed, and of course there's heating, it is a solid initially, but it turns into vapor because it's actually a sublimate. So it actually moves out as vapor and finds its way into the conical flask containing solid U on that other end, connected to a guard tube. Okay. During a class experiment, chlorine gas was bubbled into a solution of potassium iodide. State observation made. Of course, the color has to change. Why? Potassium iodide reacting with chlorine gas tells you that chlorine must displace iodine or the iodide ions from this potassium to give us now potassium chloride and iodine. See, so this is aqueous. This is a gas. It's going to be aqueous. Okay, have this. Okay, you can take this to be a solid or aqueous as well. Okay, because it's actually in solution form. So at the end of the day, the color has to change. The color has to do what? To change. You are supposed to provide a color of iodide ions while dissolved in potassium chloride solution. You see, so you can talk about a yellow color. You see, and that means the color has changed because of the iodide ions being able to actually dissolve in the potassium chloride, forming a mixture. So it is green yellow initially, the color of chlorine gas. But on dissolving into this, it displaces the iodide ions from the potassium iodide to form potassium chloride and then iodine. And the color can literally be able to actually turn orange or yellow. So at the end of the day, you must talk about the change in color. Write the ionic equation for the reaction that takes place in this case. So you can talk about potassium ions, iodide ions plus chlorine gas. If it is a gas, it does not ionize, so you can be able to actually dissociate it into ions. Then you have potassium ions, chloride ions, then plus this iodine, so that this and this will disappear. So we're going to have iodide ions plus chlorine gas. This is aqueous. This is a gas to give chloride ions plus iodine. So you can put here 2, then put here 2. So this aqueous also. This is, you can talk about solid. So that is what I'm supposed to have in as far as this part is concerned.